Okay, so in the last video we saw Planck's solution to the problem of the blackbody radiation spectrum, and his solution was based upon this idea that energy of light was quantized. So if you have light at a particular frequency nu, then the amount of energy you can have in this light is some integer times some constant times the frequency nu, and this constant is now known as Planck's constant. And Planck showed that using this idea you could successfully predict the shape of the blackbody radiation. But while his theory was successful in that regard, most physicists, including Planck himself, did not really believe that this quantization was more than some kind of just mathematical trick. Okay, so not many people believed that these units of light with energy h times nu were behaving like particles in their own right, like single point-like units of light. So what I want to talk about in this video is another piece of experimental evidence which added more weight to this idea that light indeed is not only quantized in terms of energy, but each of these units of light, the quanta as they are known, these quanta of light with energy h nu behave like individual particles. Okay. So this is the photoelectric effect, which was studied experimentally in detail by Lenard, and the explanation in terms of Planck's constant was actually given by Einstein in 1905. So we're going to go through both what the effect is and also Einstein's explanation of the effect using Planck's idea of light energy quantization. Okay, so these two pictures here describe the photoelectric effect. Basically, you have some metal plate, and you shine light onto this, light at a particular frequency. And what you find is if your light has the right properties in terms of frequency and intensity, then this can cause electrons to escape off the surface of the metal. So one way you can detect this is by using two plates like this to form a capacitor. So you attach them to a circuit with a potential difference, and then you will get a buildup of negative charge on one plate and a positive charge on the other plate. And then if you shine light onto the negatively charged plate, then when the electrons escape, the electric field between the two plates will pull the electrons onto the positively charged plate, and then they will be able to go around and complete the circuit like this. Okay. So in other words, if you're not shining light on this plate, then the electrons cannot escape. You will not get any current in this circuit. But if you shine the right kind of light on this plate and electrons do escape, then you will be able to measure this current. Okay, and this is known as the photoelectric effect because it combines light, the effect of light on electrons, right? Photo is photon for light, electric. Okay, so I'm going to talk about the results of these experiments in detail. As well as measuring the current here, you can also measure the energy of the electrons, the kinetic energy of the electrons as they move between the two plates. One way of doing that is to introduce a magnetic field here. And if you introduce a magnetic field, then the electrons feel a force which is minus the electron charge times V cross B. Okay, so in this case they're moving in that direction. So V cross B, V cross B. So down with the minus, that goes up. So the electrons will feel a force that will try to get them to curve up in this direction. Okay, and by measuring the curvature of the electron beam emitted here, you can measure the kinetic energy of the electrons. The more kinetic energy they have, the more momentum they have, and the less they will curve in response to the magnetic field. Okay. So, as well as measuring the current, you can also measure the energy of the released electrons. Okay. And in terms of the light in these experiments, both the frequency of the light used and the intensity of the light used, that just means how bright it is, were varied. Okay, and so what effect does changing the frequency and changing the intensity have on the current of the electrons and their kinetic energy? So that's the basic idea of the experiment. So the results are as follows. If you fix the frequency of light such that electrons are being emitted, and then you increase the intensity of the light, you make the light brighter and brighter, then you find that the current goes up. So that shows you that more electrons are being released. So the more intense light means more electrons. But surprisingly perhaps, no matter how intense the light is, the energy of the electrons does not increase. Okay? So having a brighter light source will give you more electrons, but it will not increase the energy of the electrons that escape. However, varying the frequency of the light does change the energy. And that's shown on this graph down here. Here the frequency of the light is plotted as a function of the kinetic energy of the electrons that escape. So the first thing is, if your frequency is too low, you don't see any electrons. Okay, so in this particular case, this blue line here, if your frequency is less than nu1, then the electrons do not escape at all. Okay, so too low frequency of light means no electrons at all. But then if you have enough frequency, and then you increase the frequency further, then you find that the electrons escape with more and more kinetic energy, and the kinetic energy grows linearly with the frequency of the light. Okay. So on this picture, nu1, nu2, nu3, this is dependent upon the metal, the material that you're using in the plate to study the photoelectric effect, and different materials have different minimum frequencies at which the electrons start being emitted. Okay. So for one metal it might be a frequency here. In order to get electrons, for another metal it might be here or here. Okay. So these are also results that classical electromagnetism cannot explain. Classically, light is a wave in the electric and magnetic fields, and the force on the electrons is proportional to the electric field and also proportional to the cross product of the electron velocity in the magnetic field. So increasing the intensity of the light should increase the size of this field, which should increase the force on the electrons. So you'd expect that more intense light, as well as being able to force more electrons off the metal, should also give them more energy, right? Because there's greater force. But that's not found. It's found that increasing the intensity does not change the energy of the released electrons. And secondly, the force here does, at least the magnitude of the force, does not depend upon the frequency classically. Okay, changing the frequency of the light will change the rate at which these electric and magnetic fields switch back and forth, but it will not change the total force, magnitude of the force on the electrons. So it's not clear why frequency should have the effect that it is observed in this graph here. Okay. So classical electromagnetism is not good at explaining the results of the photoelectric effect. Okay, it fails basically. But Einstein came up with a very simple argument to show that if you accepted Planck's idea about the quantization of light energy, and if you believed that these quanta, these units h nu, behaved as individual particles, then you could explain all of these results very nicely. Okay, so that's what I'm going to briefly run through now. Okay, so this is Einstein's explanation of the photoelectric effect. Okay, so it's based upon a number of assumptions. So first, as I've already said, you assume that these quanta of light behave like individual particles. Secondly, you assume that electrons are able to absorb these quanta, these particles, and when they absorb them, the energy of the light is transferred to the electron. Okay, so before I go any further, these particles later on got the name photons, which we've already talked about. So I will use the term photon to describe these particles. So electrons can absorb photons. The energy, photon energy, is transferred to the electron. Okay, and finally, in order to make the theory give the right predictions, you assume that the electrons only absorb one photon at a time. Okay, so no electrons absorb 2 or 3 photons. Each electron just absorbs one photon at a time. Okay, right. So we now have to consider what this circuit looks like. So we said we had two plates like this, a negatively charged plate and a positively charged plate, and we were shining light onto the negatively charged plate here, and doing so would make an electron escape and travel across to the positively charged plate. So if we think about this from the electron's perspective, let's suppose that the plates are here. So this is the negative plate, and over here we have the positive plate. And what I want to do is to plot a graph of the electrical potential energy that an electron will have as a function of its position in this capacitor between these two plates. So here we're going to plot electrical potential energy. As a function of position of the electron. Okay, so firstly, because this plate is negatively charged, that will repel other electrons, so that means they will have a high potential energy somewhere up here. And because this plate is positively charged, they will have a low potential energy somewhere down here. And between these two plates, the potential energy will decrease linearly because the electric field is a constant in between the plates. But inside the metal, the reason the electrons don't just pop out metal all the time is because there is some potential energy benefit to staying inside the solid. Okay, they can stay close to positively charged nuclei within the metal, and therefore electrons inside the metal have slightly lower potential energy than if they were outside. So you get a drop here, and you get a drop here as well from joining inside the metal and being able to get close to these positively charged nuclei in the metal. Okay, so this blue line here is the graph of the electrical potential energy. So now let's imagine that we have an electron which is sitting here in the negative plate, and we shine a photon. So here's a photon of energy h nu, and it's absorbed by this electron. Okay, so because it's absorbed, the electron energy is going to jump up, okay, to somewhere here, And as long as this energy is greater than the height here, which is the energy benefit for the electron to go into the metal, then the electron will be able to escape. Okay? And then the electron will be able to escape, and it will lose potential energy down here, which means that kinetic energy will increase. It will accelerate, in other words, okay, until it reaches the positive plate, and then it will go around the circuit again. Okay. So the first thing is, in order for the electron to escape, it has to gain enough energy to get it over this potential barrier here between this point and this point. Okay, so if we imagine that this energy gap is given by a symbol phi, which is known as the work function of the metal, then the first point to note is the electron can only escape if the energy it gains is greater than this work function phi. So the energy it gains is just the energy of the photon, which is h nu, and this must be greater than phi. Okay. Now, if that is true, if the energy is greater than phi, then the energy it has left over will be converted into kinetic energy. Okay. So the kinetic energy of the electron is going to be equal to the energy it gained minus the energy it has to spend to get out of the metal. Okay, so you can see here that you get a linear increase in kinetic energy as a function of frequency, which is one of the observations of the photoelectric effect. So a linear increase in kinetic energy with frequency nu. Okay, and then finally, because the electrons can only absorb one photon at a time, if you increase the intensity of the light, then this increases the number of quanta, increases the number of photons you have, so that will increase the number of electrons that can escape. But because each electron only absorbs one photon at a time, it will not change the kinetic energy with which the electrons escape. Okay, because the kinetic energy is fixed by the energy of one photon. Okay, so if you increase intensity, okay, then this means you have more photons. Okay, and this means you have more electrons emitted. But because each electron only absorbs one photon, the electron energy does not change. Oops, sorry. Okay, so with this very simple model of light made up of these particle-like quanta called photons, each of which has an energy h times the frequency as predicted by Planck, we can explain all of those experimental results of the photoelectric effect. Firstly, if the frequency is too low, the electron does not get enough energy to escape the metal. If the frequency is higher than that, then the remaining energy it gains goes into kinetic energy, and this gives you a linear relationship between the kinetic energy of the emitted electrons and the frequency of the light. And finally, if you increase the intensity of the light, then this gives you more photons, which means you have more photons absorbed and more electrons emitted, and therefore greater current, but you don't change the energy of a single electron, because each electron only absorbs one particle, one photon of light. Okay, so this nicely explains all of the results of the photoelectric effect, and it was actually this work for which Einstein won his only Nobel Prize. He didn't win a Nobel Prize for the theory of relativity at all. You can speculate about why, but I probably shouldn't. But he did win the Nobel Prize for this work. And following this, it became much harder to say that these photons, these quantum of light, were just some sort of mathematical idea. Okay, because here, you really can see that the light is behaving like a particle, being absorbed one at a time by these electrons in the photoelectric effect.